Hello, everyone. Thanks for listening to my presentation. Today, I'll be talking about my paper, which is about adaptive immediate feedback can improve novice programming engagement and intentions to persist in CS. My name is Samiha Marwan. I'm a PhD student in North Carolina State University, and I have done this work in collaboration with Gilgao, Dr. Susan Fisk, Dr. Thomas Price, and Dr. Tiffany Barnes. So from the title, it looks like I'll be talking about automated feedback. And there's lots of feedback actually in literature, like misconception feedback, next step hints, auto-graders. And mostly this feedback is given to students to improve their performance and maybe learning. But what about students' motivation and engagement and persistence in programming? What about these effective outcomes? So let me tell you why this might be important. So imagine this is a student who is working in a homework in a block-based programming environment. So, and this environment also can give them feedback. So while student is working, maybe he did not know how to start or if they are in the correct direction or not. So they requested the feedback. So when they requested the feedback, they got a feedback and it was correct. But it told them to use a custom block, and maybe custom block which is a function, and maybe students are not really aware of what does it mean or what is that. So maybe they do not understand it, and maybe this makes them even feel more frustrated and confused. And there's literature that showed that some automated feedback can make students confused and frustrated. So as a tutor, what will you do to avoid students' confusion or just help them keep going? So for me, I might just say, keep going, you're on the right track. Or I might even say, let me break down the problem for you by just giving them some sub-problems, and maybe this will help them to think better about the problem and progress. Also, there's other specific features of the feedback to be effective. For example, it has to be immediate to what the student is doing, and also specific, like related to also what the student is doing. It has to be positive, like to tell them that if they did something correct, to just confirm the correctness of this step. And also to be corrective, like when a student makes a mistake. So these feedback characteristics have been shown to be effective in human teaching dialogues and to improve students' motivation, confidence, and it even correlates with student learning. So wouldn't it be really awesome if the computers knew how to do that too? And this is my goal of this paper. I want to understand how an adaptive immediate feedback not only improves students' performance and learning, but also if it improves students' perceptions, engagement, and intentions to persist in CS. So let's talk about the design of the system. So first of all, we wanted to know or to keep track of what the student is doing. So we divided each task into a set of objectives. For example, this is a task. It asks the students to draw a polygon given a number of sides from the user. So for example, these two blocks mean that it refers to one objective, which is to get the number of sides from the user and use it in the repeat block. And then for each objective, we developed implicit auto-graders. And while the student is working, these auto-graders keep detecting which objective has been completed or not. So in order to communicate this feedback, we developed another two features. First of all, it's about messages. And we actually provide these messages to students while they're working to keep them engaged and motivated to finish. To design these messages, we asked several high school students to construct encouraging messages to motivate a hypothetical friend in two situations. When your friend is struggling and when they did something correct during programming. So this is how the pop message looked like. So this is a student, he used this block and then that block and then that block. Looks like they did an objective. So the system will say, you're legit amazing. So this is kind of a message that will be given to students. It's not from me. It was suggested by the high school students. And then the progress panel, which is our second feature. And unlike the pop-up message, this feature is stuck on student's screen. So initially, all the objectives are deactivated. And if they completed any of the objectives, it will be highlighted in green. And if they broke any of them, it will be highlighted into red. So let's see a demo of how this looks in practice. So this is iSnap, a block-based programming environment. And while a student is working, looks like these are the objectives and they're working with one of them. And then, oh, they finished one objective and the system highlighted it to be green and give them a book message too. So that's great. The student kept working and then they used another block and then they remove a block. Oh, looks like they missed something. They break something. So they break this objective, and that's why the system highlighted in red. Then the system, the student returned back this block, and oh, now the system told them, yay, it is fixed, which means that looks like the pop-up message was contextualized based on what the student is doing. So it noticed that this objective was done before, but it was broken, and then the student did it again. So this looks cool, and that's why I wanted to evaluate if it has also cool results or cool impact on students. To do so, we had a pilot study where our population were 25 high school students who participated in 2 summer camps. And we divided students into 2 groups. The first is control group, where they only have hints, which are just next step hints suggested by the system. And the other group is the experimental, where they have hints plus the AIF system, or the adaptive immediate feedback system. In the camp, students started by having an introduction to SNAP, and then a pre-survey and a pre-test, and then they have 2 programming tasks, and then they have a post-survey and a post-test, and then they have task 3, where no feedback was given, just as a measure of learning, as I will talk about soon, and then I ended up by having interviews. So, to understand students' perceptions of each features, we transcribed these interviews and we did thematic analysis on them. So for each feature, I asked students how it was helpful, how it was less helpful, and how can we improve it. For the pop-up message, we found that it was perceived differently across genders. So for example, female students noted the funny aspects about it, like they're funny, they help me to keep going, and it's better than just saying correct because it gets you more into it. While male students, I think all of them gave me the same answer, which is, it just told me that I am on the right track. For the progress panel, all students appreciated it, and even they requested to have it in future tasks. For example, one female student said that it helps you to pace yourself. So if I didn't have this, I would probably be more frustrated. So our measure here, our first measure in the quantitative analysis is what is the impact of the AF system on students' intentions to persist in CS. To do so, we use the linear mixed effects model, and we have 3 factors. First, within subjects factor, which is the time, so the pre-survey and the post-survey. And then the between subjects factor, which is the pre-test, and we use this as a measure of students' prior knowledge, like 0 if they have low and 1 if they have high, and then the AF system. And I want to note here that this variable for the AF was 0 for in the pre-survey time, because at this time, no students have used the system yet. So we have 50 observations, and we found that the AF system significantly improves student CS persistence. And to give more context, we found that the average students in the AF has 9.4 points higher than that of the control group. And actually, we did not find an effect of the prior knowledge, which is the pre-test, or even the time, which means that this only happens when students use the AF system. I also want to highlight that this was one of the primary contributions in our work. So this is the first study to present evidence that automated feedback can improve students' intentions to persist in CS. So this was cool. Our second result is about students' engagement, and we measured engagement by measuring the percent of time that students spent idle. So if students spent more time idle, this means that they were not engaged, but if they spent less time idle, this means that they were engaged because they are working more with the system. And also here we found that the AF group were more engaged, like they spent significantly less idle time than the control group, and also we did not find an effect of prior knowledge. So this graph here showed the big difference of the idle time spent by the experimental group in comparison with the control group. And also this result is consistent with uncertainty reduction hypothesis by Mitrovic et al. And also it is consistent with our qualitative analysis. So for example, some students tell us this system gives you motivation, you can see how far you are and how much you have to do. And maybe that's why they were not spending really much idle time like the control group. Our third measure here is students' performance. And to measure performance, we used each objective in each task as an observation in our model. So we have 25 students and we have 8 objectives, making a total of 200 observations. And for each objective, we just calculated if it was complete, like 1, or not complete, 0. And I want to highlight here that these observations are nested within participants. So using a linear probability model was appropriate to predict the likelihood that a student completed an objective. So we found here that the AF system has a marginally significant effect on performance, and that students in the AF system were 13.1% more likely to complete an objective than students in the control group, as you see here from this table. And also we did not find an effect of prior knowledge. For learning, we used the same model, but for task 3, where no feedback was given. This task has 5 objectives, and we have 25 students making a total of 125 observations. And again here, we found that the system has more than significant impact. The p-value was 0.056. And to give more context, we found that the students in the AF system were 25.4% more likely to complete an objective than students in the control group. And again, we did not find an effect of prior knowledge. So to conclude, our goal in this paper is to develop a system that can provide automated feedback, not just to support students' performance and learning, but also to support students' desire to be a programmer. And the main takeaway here that I want to communicate this and say that the CS education community should start thinking about how can we improve students' attitudinal measures using the automated feedback. For example, like intentions to persist, persistence, and self-efficacy. So for my future work, I designed our design system. Actually, it requires extensive effort to be built by experts to design it, to develop it, to test it. And for me, it took me around 48 hours to do that only for 2 exercises. So actually, this will be really hard to implement for longer programming tasks. So is there an easier way to detect that? So in my recent work, we explored using automated data-driven features instead of automated expert-authored objectives. And we are still exploring more on that, but stay tuned for more. Thank you so much. I appreciate your time, and I'll be happy to hear your questions. See you there.